Right, we're going to now start with question number 7. So, copper 2 complexes are colored. The color is caused by the d electrons of copper moving from their ground state to the excited state. So, explain why aqueous solutions containing copper Cl4 2- ions are yellow. So, there's 2 marks in here. So, when a visible light hits a transition metal, as electrons jump up to the higher orbitals, some frequencies are absorbed depending on the size of the energy gap, delta E. The rest of the frequencies are reflected, and the color seen here is yellow for this complex ion. So that's what you see. So whatever gets reflected, that's what you see. 7.2. So you got when an electron moves from a ground state to excited state in a copper complex, the energy change is this value here. Sorry, I just messed up there. Okay, so it says the Planck constant is its value. The calculated frequency in seconds minus 1 of the light absorbed. So you need to know the formula. Delta E equals to H V equals to HC. I think that's lambda. So that every bit here I explain what is meant. So you have the C is the speed of light, the H is Planck's constant, like here. The V, this little V is frequency of light absorbed. Sorry if I don't explain the V very well. It's the frequency of light absorbed, and then this sign here, wavelength of the light absorbed in meters. So this is the formula used. So we know that delta E is this value here, and we know the Planck's constant, so we can work out the frequency. So if you do that divided by that, gives you that. So that's how you do this calculation. Okay. State 3 ways in which a transition metal complex can be changed to alter this color. So you can, there's 3 things can happen. So you can change your oxidation state of metal. So it goes from, for example, 2 plus to 3 plus or something like that. Change of ligands. So the ligand, if you can go from, like, for example, 6 ligands to 4 ligands. Change your coordination number is how many ligands is, no, sorry, I made a mistake here. Change your ligand to type of ligands, and this is coordination number is how many ligands are attached to start with, and the one is finished with. Okay, so that's how you answer that first question. Right, next bit here is consider the following reaction scheme. P, Q, and R are different complex ions copper. So that's how they are. So you got CuCl4 aqueous. So you have excess water, you get P. Then you add the Na4, the EDTA, and you get this R. Here you add excess aqueous ammonia and you get this Q. Name the shape of CuCl4. So that's tetrahedral because there's 4 bonding pairs, no lone pairs. Give ionic equation conversion CuCl4 2- complex ion P. So it goes from here to here. If you add water to it, you end up with 6 waters inside and 4 Cl- comes out. And it says state the color of solution containing complex Q here. Give ionic equation for conversion this into Q. So first of all, the color that it changes into is deep blue, and you just have to know that. You have to memorize it. And the equation is CuCl4 2- plus 4NH3, because excess for copper is always 4, no more than 4. That means you add 2 waters X to make 6. Then you end up with this complex ion plus 4 Cl-. Okay. Identify complex ion R. So you got, if you have that plus EDTA, which is this one here, plus EDTA, you end up to, everything comes out, and then you go Cu EDTA 2-, because Cu is 2 plus, EDTA is -4, it gives you equals to -2, 2 over 2-. Okay. Right, question 8. This question is about cells. The half equation of 2 electrodes combined to make a non-rechargeable cell are this and this. Identify oxidizing agent. The oxidizing agent is the one that gets reduced, so it has to be MnO2 because that's more positive, so that one is reduced. This shows a cross-section of rechargeable silver zinc cell. So it says, suggest a function of the polar separation figure 1. Well, allows ions to move across. So this porous here, which says a polar separator, allows ions to move across. A standard electron potentials for two half equations for silver zinc cell are these two. It says, given equation for the overall reaction that occurs in cell is recharging. Okay, so usually you add them together by putting the most negative is the oxidizing one and the most positive is the reducing one. So you put that is correct way, that flicks the other side. But because it's recharging, that's the opposite, that is going to be the opposite cell. So you have to flick the cell around to the other side. So you add them together when you flick this, and then you put it the other way around because it's recharging. So the MF of alkaline hydrogen oxygen fuel cell is this value. The standard electrode potential for one of the electrodes in an alkaline hydrogen solution of fuel is this one here. Give the half equation for the other electrode and calculate standard electrode. So you got, this is the other one, and you have to learn it, you have to know it, otherwise you won't know it. O2 plus 2 H2O plus 4 E electrons gives you 4 OH aqueous. Then if you want to calculate the the heat cell is always the at the most, so the E cell reduced minus, so if you want to calculate the EMF, so if you want to calculate, you got the EMF, the value is 1.23, which is this value there, for the E value there. So E reduced minus E oxidized. So we need to know if this one is reduced or oxidized, because that one is the reduced one, because the electrons goes in there. That one is the oxidized one, goes to the other side. So when you add them together, it becomes overall equation. So then if you say 1.23 equals to E reduced minus E oxidized, that you know is that one there. So when you add them together, you end up with E equals to 0.4 volts. And the next one, it says, suggest why EMF values of acidic and alkaline hydrogen fuel cells are the same, because they both have the same overall reaction. So when you add the acidic one or the alkaline one, always gives you the overall of 2H2 plus O2 gives you 2 waters.